Before we start the presentation, I want to make a note that this presentation can be broken up into roughly two parts. The first part is going to contain background information. And so we're going to include all of the necessary definitions to define a Psyquandle and to study these singular knots and pseudo knots with Psyquandles. So those ideas are mostly presented in the paper Psyquandles, singular knots, and pseudo knots. Once we do the background, we're going to move over and make these enhancements to the Psyquandle counting invariant, and we're going to be using some weight functions. So this idea was joint work with Sam Nelson, and it's in the paper Cocycle Enhancements of Psyquandle counting invariants. At the end of this presentation, I'm going to include a full reference for your convenience, but for now, just keep in mind that the presentation can be broken up into two pieces. So the first half is just a background, and then we'll get to the enhancement in the second half of the presentation. So in this presentation, we're going to be focused on singular links and pseudo links. First, we're going to introduce the definition of a singular link. So a singular link on n components is the image of a smooth immersion of n copies of S1. And you can have finitely many singularities, which are called singular crossings. So we can think of these singular crossings as being the result of two of these strands of a knot, or if you're thinking of a link, getting stuck together in a fixed position. And this is going to be really important that when they get stuck, you're not allowed to rotate them. So we'll come back to this idea. But again, a singular link is just a smooth immersion of n copies of S1, and this allows for these finitely many singularities that we call singular crossings. Throughout this presentation, we're going to be mentioning singular links. Whenever we mention singular links, we actually mean oriented singular links. So how do we get an orientation on a singular link? Well, the orientation on each S1 induces the orientation on your singular link. And so in this presentation, we're only going to be considering singular knots and links with orientation. The next thing to note is that we're not going to be working with the singular link itself. We're going to be working with diagrams of these singular links. So we're going to be referring to these as singular link diagrams. So in a singular link diagram, you have both the classical crossings and you have four valent vertices. So for these four valent vertices, we require that there's a fixed cyclic ordering around the vertices. So when you take a look at these singular link diagrams, we're going to see the classical crossings, so the positive and negative crossings that we have down at the bottom of this slide. And we're also going to have this third type of crossing. And this is going to be the singular crossing, and it's going to be denoted by two strands crossing each other with a point. And this is going to denote that this is a singular crossing in our singular knot diagram. So here we have two examples of singular knot diagrams. The one on the left is the classical trefoil. So here we can consider this a singular knot diagram with 0 singular crossings and 3 classical crossings. But in any case, we can think of this as a singular knot diagram. As I mentioned earlier, we're only going to be considering singular knots and links with orientation. So in terms of the diagram, we're going to be denoting the orientation with an arrow on the strand or strands of our singular knot diagram. On the right, we have another singular knot diagram. Here we have 3 crossings. 2 of them are singular crossings, And the third one is a classical crossing. And again, we have an orientation on this diagram, meaning that this is representing an oriented singular knot. So the next thing we're going to do is we're going to define pseudolinks and pseudolink diagrams. And the reason is that the invariants that we're going to be defining are similar for these two types of knots. There is a difference, and we're going to note the difference, but for the most part, there's a giant overlap. And so we're going to be defining these invariants for both singular knots and pseudo knots. So now a pseudo knot is a knot or a link that contains classical crossings. So the classical crossings we're used to, but it also contains pre-crossings. So a pre-crossing is a classical crossing, but we just don't know any information about which strand goes over and which one goes under. So we lose the information of the over and under at a crossing. So in terms of the diagram for a pseudo knot or pseudo link, we're going to have these pre-crossings drawn as undecorated self-intersections. So here's an example of how we're going to represent a pre-crossing. So this is just going to be the two strands intersecting with no point at the intersection. So remember that the singular crossing is going to be denoted by the two strands intersecting and a point at the intersection. But for a pre-crossing, we're thinking of this as a classical crossing. We just don't know any information about the over and under of these strands. So this is just an undecorated self-intersection. So here we have some examples of pseudo-link diagrams. The diagram on the left is a pseudo knot diagram, and it looks similar to the trefoil, except here we don't have any information at the crossings. So in terms of the overstrand and understrand, we don't have any of that information. Every crossing here is a pre-crossing. And we also have an orientation, so when we're going to be considering these pseudo knots and links, we're going to be considering pseudo knots and links with orientation. And so in terms of the diagram, we're going to denote the orientation, again, by an arrow on the strands. The diagram on the left is a pseudo link. Here we have two components. One component has the pre-crossings, and then it's linked with an unknot. And again, here we're going to be considering these oriented pseudolinks. So in terms of the diagram, we have orientations on each component. Since we're going to be studying singular knots and pseudo knots by their diagrams, then we need to introduce the Rightomizer moves for both singular knot diagrams and pseudo knot diagrams. Before we introduce those Rightomizer moves, let's go ahead and recall the Rightomizer moves for classical knots. So at the end of the presentation, you're going to be able to find this reference, but if you want to find a generating set of oriented Rightomizer moves, so this is for just the classical case, then you need the following two type 1 Rightomizer moves. So here I have them listed as R1A and R1B. You also need a type 2 move, so here we have it listed as R2A. And we also need a type 3 Rightomizer move, and this is R3A. So if you have this set, then this is going to generate all of your oriented Rightomizer moves. So you only need to consider these 4 Rightomizer moves to generate all of your oriented Rightomizer moves. Since we're interested in studying singular knots and links, and we're going to be doing this with the use of singular link diagrams, well, we need to introduce the Rightomizer moves for these types of diagrams. And so if we were just considering classical knots and classical knot diagrams, then the generating set that we just introduced would be enough. In the paper here that I cite, it was shown that the classical Ridermeister moves plus these 3 additional moves that I have listed here generate what's known as the generalized Ridermeister moves. These are the moves that we need in order to use our singular link diagrams. And so here we see that we have 2 type 3 moves that are similar to the classical case, but one of the crossings is replaced with a singular crossing. And for the first one, we have that the overstrand goes over this singular crossing. And in the second type 3 additional move, we have that the understrand goes past the singular crossing. In the third move that we're adding, this is similar to a type 2 Rightomizer move, but here we've replaced one of the crossings with a singular crossing. So again, in the presence of the classical Rightomizer moves, you only need to add these 3 moves in order to generate the generalized Rightomizer moves, and those are the moves we need for singular link diagrams. So now that we have that the generalized Rightomizer moves are the Rightomizer moves needed for singular knots and links, well, we can start talking about the Rightomizer moves for pseudo knots and links. It turns out that these 2 sets are pretty similar. So if you consider the generalized Rightomizer moves, and wherever you see a singular crossing, you replace it with a pre-crossing, and you add the following 2 additional moves, what we get is a set of Rightomizer moves for pseudo knots. So again, if you consider the generalized Rightomizer moves and you replace the singular crossings with pre-crossings and you add these 2 additional moves, you get a set of Rightomizer moves for pseudo knots and pseudolinks. Before we introduce the definition of a Psyquandle structure, I want to make the following note. The original definition of the Psyquandle structure first appeared in the paper Psyquandles, Singular Knots, and Pseudo Knots. The definition that we're going to be using in this presentation is a slight reformulation, and this reformulation of a Psyquandle structure appears in the paper Cocycle Enhancements of Psyquandle Counting Invariants. So just keep that in mind, that this definition that we're going to be using is a slight reformulation of the original one. And the reason that we reformulated the definition of a Psyquandle was to make the axioms that we need for the weight functions be a little bit nicer. So the original definition is slightly different than what appears in this presentation. So let's go ahead and define a Psyquandle structure on a set. So here X is going to be our set. A Psyquandle structure on this set is going to be a set of 4 binary operations. These operations are denoted by under triangle, over triangle, under dot, and over dot. These 4 operations have to satisfy the following 6 axioms. The first axiom is listed as axiom 0, and this is just saying that the 4 operations are right invertible. And we're going to be using this right invertibility of these operations to make our weight function axioms that we're going to be defining later on a little bit nicer. So this is a slightly different presentation of a Psyquandle than the original definition of a Psyquandle structure. But here we have that these 4 operations are invertible, and then these operations satisfy the following 5 axioms. So you have 1, 2, 3, 4, and 5. So if you have your Psyquandle structure satisfying axiom 0 and then 1 through 5, well, those axioms are motivated by the generalized Rightomizer moves. So if your hope is to get an invariant of singular knots or links, then all you need is a Psyquandle structure on this set X. But if your hope is to get a pseudo knot or pseudo link invariant, then you need to add an extra condition. So this extra condition comes from the additional move that looks like a type 1 move where the crossing is replaced with a pre-crossing. So in that case, we have a Psyquandle structure on X, and if it satisfies the equation that X under dot X is equal to X over dot X, and this is for all X in our set X, then we say that this Psyquandle is P1 adequate. And so when you want to get an invariant of pseudo knots and pseudolinks, then you need a P1 adequate Psyquandle. So again, the axioms of a Psyquandle are motivated by the generalized Ridermeister moves. And this is if you're interested in defining an invariant for singular knots and links, then that's all you need. But if you're trying to define an invariant of pseudo knots and links, then what you need is a P1 adequate Psyquandle, and the axioms for a P1 adequate Psyquandle are motivated by the set of Rightomizer moves for pseudo knots and pseudo links. And so instead of reading the axioms line by line, what we're going to do is give a description of how you go from the Rightomizer moves to the axioms. So the list of axioms are here, and you can pause and go back to carefully look through the axioms. But I think the more important part is how do you go from the Rightomizer moves to the axioms. So before we take a look at how we would go from the generalized Rightomizer moves to the axioms of a Psyquandle, or the set of Rightomizer moves of a pseudo knot to the P1 adequate Psyquandle axioms, well, we want to know that there's actual operations that satisfy all of the axioms to be a Psyquandle. And so in the paper Psyquandles, Singular Knots, and Pseudo Knots, the authors define the following family of Psyquandles. So this is known as an Alexander Psyquandle. And the Psyquandle is not just a Psyquandle, it's a P1 adequate Psyquandle. So if you're trying to define an invariant for pseudoknots, you can use an Alexander Psyquandle. Of course, you can also use this to define an invariant of singular knots. So later on in this presentation, we're going to be using a specific Alexander Psyquandle to compute sort of the nicest invariant that you can get out of these Psyquandles. So that's known as the Psyquandle counting invariant. So we'll do that in a little bit. And then also we're going to use a specific Alexander Psyquandle to compute the Cocycle enhancement of that counting invariant. And so that'll be at the end of the presentation. So most of the Psyquandle structures that Sam and I were dealing with in the paper Cocycle enhancements of the Psyquandle counting invariant were not as nice as the Alexander Psyquandle. So we didn't have nice expressions. What we had were these operation tables. So we found the Psyquandle structures using Python code, and the outputs were in the form of operation tables. And so you can encode these operation tables by a block matrix. So each block corresponds to an operation. And the nice thing about these block matrices that encode the operations is that if you look at the last two blocks and you look at their diagonal, if the diagonals agree with each other, then this means that you have a P1 adequate Psyquandle. And so this gives you a nice visual to check and see if your Psyquandle is P1 adequate. So here we have a P1 adequate. The last two blocks have identical diagonals. We have 3, 1, 2. And so this is a P1 adequate Psyquandle. So we're going to be using both of these. We can represent the operations with these block matrices, or if we have a nice expression, we can use the expression to define the operations. So now that we know that there are operations that satisfy the axioms to be a Psyquandle, and also operations that satisfy the axioms to be a P1 adequate Psyquandle, well, we want to get back to the idea of how do you go from the generalized Rightomizer moves to the axioms, or if you're dealing with the set of Rightomizer moves for Pseudolinks, how do you go to the axioms of the P1 adequate Psyquandle? So the first thing we have to do is we have to define the idea of a coloring. So a coloring of a singular link or pseudolink by a Psyquandle or P1 adequate Psyquandle is a function. And this function goes from the set of semi-arcs of a fixed diagram of your link. So whether you're thinking about it as a singular link or a pseudolink, you have to fix a diagram. And now the following rules are going to tell us how to assign our operations at these different crossings. So first, for a positive crossing, so this is the figure on the left, if we start with the left semi-arcs colored by X and Y, as X goes under Y, the output is going to be X under triangle Y. And on the right, for the overstrand, well, we have Y over triangle X. So you can sort of think of these operations as telling you that Y is over X and X is under Y. So in a similar fashion, if you have a negative crossing, you're going to be using your under triangle operations and your over triangle operations. And so this gives you the exact rule for a negative crossing. So this is the figure in the middle. And then on the right, we have an intersection of these two strands. So here, depending on whether you're looking at a singular link, then it would be a singular crossing here. So we would put a point to indicate that this is a singular crossing. If you're dealing with a pseudolink, then it would just remain undecorated. But in any case, if you start with the left semi-arcs colored by X and Y, then the right semi-arcs get assigned the following operations. So the top right is Y over dot X, and the bottom right is going to be X under dot Y. So in addition to the rules at a positive crossing, a negative crossing, and either a singular or pre-crossing, we also have some coloring rules for the inverse operations of under triangle, over triangle, under dot, and over dot. And here are the coloring rules for these inverse operations. So now that we have our coloring rules set up, now we can think about how to go from the generalized Rightomizer moves to the Psyquandle axioms, or the set of Rightomizer moves for pseudolinks to the set of axioms for a P1 adequate Psyquandle. So as mentioned earlier, the definition of a Psyquandle structure presented here is the definition in the paper Cocycle Enhancements of the Psyquandle counting invariant, which is a reformulation of the original Psyquandle definition. And specifically, we reformulated axiom 4. So let's take a closer look at axiom number 4. And we're going to do this by considering a specific move in the list of generalized Rightomizer moves. So here we have this move that looks similar to a classical type 2 Rightomizer move. But if you take a look a little bit closer, we see that we have in both of these diagrams one either singular crossing or pre-crossing, depending on whether you're thinking of this as being part of a singular link or if you're thinking of it as part of a pseudo link. So here, so if we start with the figure on the left and we color the top two left semiarcs x and y, and we use our coloring rules that we just introduced, then we can get the colorings for the rest of the semiarcs. So for example, on the top right semiarc, we get y over triangle x, and below that we get x under triangle y. And then from there, we use the coloring rule for the inverse operations to get the output strands or the output semiarcs. So now if we consider the figure on the right, well, these two have to be equivalent. So this is a type of Rightomizer move. It's a generalized Rightomizer move. So these two should be equivalent before and after. So this means that the input semiarcs should be colored the same. So we have x and we have y over triangle x at the top. At the bottom, we should have the same outputs. And so we colored those. And then using, again, our coloring conventions or rules, we can get the rest of the semiarcs colored. So now, once we have everything colored, we see that this move gives us axiom number 4, or it gives us axiom number 4 as it's formulated in the definition of the Psyquandle structure. So now to get the remaining axioms, you have to go through the Rightomizer moves, color them, and see the equations that you get following the coloring conventions at a positive, negative, singular, or pre-crossing, and the coloring rule that we have for the inverse operations. So if you go through the Rightomizer moves and the 3 additional moves for the generalized Rightomizer moves, then you get the axioms for a Cyclone. So now if you're considering Pseudo Knots, you also have to take into account the additional Rightomizer moves. So that'll give us the P1 adequate Psyquandle condition. So now we're going to introduce a really useful concept. So this is going to allow us to define an invariant for singular knots and for pseudo knots. And this is going to be an invariant that we can actually compute. Before we introduce that idea, what we have to do is we have to define the idea of a homomorphism of Psyquandle. So a Psyquandle homomorphism. So we're going to let x and y be finite Psyquandles, and we're going to have operations under triangle, over triangle, under dot, and over dot. And these are going to be different for the Psyquandle x and the Psyquandle y. And so a map from the Psyquandle x to the Psyquandle y is a Psyquandle homomorphism if it satisfies the following conditions for all x and y in X. And so this is just saying that the map respects the Psyquandle structure. So now that we have the idea of a Psyquandle homomorphism, we can start to talk about these colorings of the diagrams of singular links and pseudolinks by maps instead of just the labeling of the diagram. So here D is going to be a singular link or pseudolink diagram of some singular link or pseudolink. So we have that for every singular link and pseudolink diagram D, there's an associated fundamental Psyquandle of that diagram. And this is denoted by P of D, or in the case when you have a P1 adequate Psyquandle, then we have P subscript 1 or I of D. The fundamental Psyquandle of this diagram D is the quotient of the free Psyquandle on the set of semiarcs of your diagram by the equivalence relation generated by the relations determined by the crossings in the diagram. And so in the paper Psyquandles, Singular Knots, and Pseudo Knots, the authors of that paper proved that the isomorphism class, and this is denoted by P of L, where L is a singular link of the fundamental Psyquandle of the diagram D, is in fact an invariant of oriented singular links. Similarly, if you have the isomorphism class denoted by P subscript I of L, where L is a pseudolink of the fundamental P1 adequate Psyquandle of the diagram, that's going to be an invariant of oriented pseudolinks. So now with the idea of the fundamental Psyquandle, well, we can think about these colorings a little bit differently. So the assignment of the elements of the Psyquandle, so the Psyquandle is X, to the semiarcs in the diagram D that you're using for your singular link or pseudolink defines a homomorphism. So this is some map which is a homomorphism from the fundamental Psyquandle to the target Psyquandle. And this is if and only if the coloring rules that we set up at the beginning are satisfied at each crossing of your diagram D. And so each one of these maps, F, is going to be called an X coloring of your diagram D. So now that we have these X colorings, well, instead of having to compute or find the fundamental Psyquandle of your link, well, what we can do is compute the following. We can compute the set of Psyquandle homomorphisms from the fundamental Psyquandle to a target Psyquandle. And this target Psyquandle can be finite. And so the way we would compute this set of homomorphisms would be just to compute the set of X colorings of your diagram D that represents your either singular link or if you're using pseudolinks. So this gives us a really nice computable invariant. So if we compute the set of X colorings of your diagram D of your singular link or pseudolink, we can take the cardinality of that set, and this is going to be what's known as the Psyquandle counting invariant. So this is an integer valued invariant for singular links and pseudolinks. Of course, this depends on whether you have a P1 adequate Psyquandle or if you're just using a Psyquandle. So now let's take a minute to see how we would compute the Psyquandle counting invariant. So the first thing we're going to do is we're going to pick a Psyquandle structure on the set X, and here X is going to be Z5. And so the operations that define our Psyquandle structure are given to us in this block matrix. So we have basically encoded in here the operation table for each operation that make up our Psyquandle structure. So we're going to be using this Psyquandle, and we're going to be computing the Psyquandle counting invariant of the following link. And this is a singular link. So this is a 2-bouquet graph of type L, and this is listed as 1 subscript 1 superscript L, and this is in this paper. So now the first thing we're going to do is we're going to fix an ordering on the semiarcs. So we're going to call them X1, X2, X3, and X4. Once we have that, well, now we have our coloring rules, and so we can use our coloring rules for singular crossings and our classical crossings to get the following coloring equations. So we get a system of coloring equations. So now it's a matter of solving this for some solutions, and it turns out that this system has 5 solutions. So since the system has 5 solutions, this means that each one is going to be an X coloring. So it's going to be a coloring of this singular link diagram by the chosen Psyquandle. And for each one of these X colorings, well, we can represent this as a map. So this is the homomorphism from the fundamental Psyquandle to the target Psyquandle, and we can represent this as a 4-tuple. So here we compute the set of homomorphisms from the fundamental Psyquandle to the target Psyquandle. And then if we want to compute the Psyquandle counting invariant, all we have to do is take the cardinality of this set, which is 5, because we have 5 colorings of this singular link by the chosen Psyquandle. And so this gives us a really nice computable invariant for the singular knots. Again, if we were dealing with pseudo knots, then we would have to consider a Psyquandle that's P1 adequate and then do the same process. So now that we have this Psyquandle counting invariant, the main goal of the paper where we were looking at enhancements was to define a cocycle enhancement to the Psyquandle counting invariant. So the approach we took was similar to the approach taken before in the case of biquandles. So there's a biquandle 2 cocycle invariant that enhances the biquandle counting invariant. So in this case, we wanted to extend that to the case of Psyquandles. So here we should note that if you look at the axioms for a Psyquandle and you consider axiom 0, 1, 2, 3, that defines a biquandle. And so what we're going to be doing is we're going to be combining a biquandle 2 cocycle plus an extra function, and we're going to define this cocycle enhancement of the Psyquandle counting invariant. So if you're interested in seeing the full construction of the biquandle homology and cohomology, and also the construction of the biquandle 2 cocycle invariant for classical knots, then I'll refer you to this paper. The main thing that we need is that this biquandle 2 cocycle is in fact an invariant. So we're going to be using this biquandle 2 cocycle, and I'll point it out once we come across the biquandle 2 cocycle. So the way we're going to enhance the Psyquandle counting invariant is by introducing 2 functions. So here X is going to be a Psyquandle, and R is going to be a commutative ring with identity. So we're going to say that a Boltzmann weight for the Psyquandle is going to be a pair of maps. So we're going to have phi and psi, and these are going to go from the Psyquandle cross Psyquandle to our commutative ring denoted by R. And these 2 functions have to satisfy the following axioms. So axiom 1, 2, and 3. Here we should note that if you consider axiom 1, so this is saying that phi of x is equal to 0. And then if you look at the first equation in axiom 3, well, this only involves the map phi. And so what we have here are the 2 conditions that you need in order for phi to be a biquandle 2 cocycle. And so we have that phi is our biquandle 2 cocycle, and then we're adding this psi function. And psi has to satisfy conditions where you have both phi and psi. So in the case where X is P1 adequate, so when you're going to be defining an invariant for pseudolinks, then we say that phi and psi are P1 adequate if psi satisfies the following condition. So you have that psi of x is equal to 0. So again, How do we get these axioms? So similar to the case of a Psyquandle, these Boltzmann weight conditions or axioms are motivated by the Rightomizer moves. So if you're considering singular links, then you're going to consider the generalized Rightomizer moves. If you're considering Pseudolinks, then you're going to consider the generalized Rightomizer moves plus the extra type 1 move with a pre-crossing. So as I mentioned, the Boltzmann weight axioms are motivated by the Ridermeister moves. And of course, depending on what kind of knot you're considering, you're either going to look at the generalized Ridermeister moves or the generalized Ridermeister moves plus that type 1 move with the pre-crossing. And so what we have to do is we have to set up the weight contribution for each one of these crossings. So at a positive crossing, we're going to assign a positive phi, and we're going to be taking in the colorings on the semiarc on the left, so x and y. Similar, at a negative crossing, we're going to assign negative phi, and we're going to take in the inputs in this order for the left side of the semiarcs. And then at a pre-crossing or a singular crossing, we're going to be assigning this new weight function that we're calling psi. And we're going to be plugging in x and y, and these are the colorings on the semiarcs on the left. So these are our weight contribution rules that we're going to be following. If you take the Rightomizer moves and you color them by a specific Psyquandle, and then you follow the weight contribution rules, then you're going to be able to extract the axioms for the Boltzmann weight of a Psyquandle. And so instead of looking through all of them, let's just look at a fairly simple one. So let's look at the condition we need for a P1 adequate Psyquandle and the corresponding Boltzmann weights that are P1 adequate. So we're going to look at this extra type 1 move where we have a pre-crossing. So since here we have a pre-crossing, we're going to be assigning the psi function, and the inputs are going to be x and x. And so here, since this is the equivalent before and after this move, what this is saying is that the weight contribution of this Rightomizer move is 0. So this means that psi of xx should equal 0. And that's exactly our axiom for our Boltzmann weights to be P1 adequate. And so if you go through the generalized Rightomizer moves, you color them with your Psyquandle, and then you follow the weight contribution rule, you're going to get the axioms for our Boltzmann weights. So now the question becomes, how are we going to use a Boltzmann weight of a Psyquandle to enhance the Psyquandle counting invariant? So let's go ahead and set that up. So here we're going to be considering some Psyquandle, and of course, depending on what kind of knot or link you're considering, this is going to either be a Psyquandle or a P1 adequate Psyquandle. Next, we're going to have R be a commutative ring with identity, and we're going to have our pair of weights, so our Boltzmann weights, so we're going to have phi and psi. And of course, if we're considering a P1 adequate Psyquandle, then we need the Boltzmann weights to also be P1 adequate. So now D is going to be an oriented singular link diagram, or potentially an oriented pseudolink diagram. And this is going to be representing some singular link or pseudolink that we're going to describe, or we're going to denote by L. So now that we have our Psyquandle chosen and we have our Boltzmann weights for that chosen Psyquandle, what we're going to do is we're going to compute the X colorings of our diagram. So again, this is the map or a homomorphism from the fundamental Psyquandle to the target Psyquandle. And so we're going to compute the Boltzmann weight of the X coloring. And so this is going to be denoted by BW of F, where F is an X coloring. And in order to compute this Boltzmann weight of the coloring, we're going to do this by taking the sum over all crossings in our diagram D. And we're, of course, going to be following the weight contribution rule that we set up earlier. So this is going to be the same weight contribution rule that we set up. So again, first we have to compute the X coloring. So we have to find the colorings of the diagram by our chosen Psyquandle. Once we have these X colorings, we compute the Boltzmann weight for each coloring. And so now we can define a single variable Boltzmann enhanced Psyquandle polynomial. So this is going to be the enhancement to the counting invariant. And so the way this is defined is that we pick a variable that we're going to call W, and we're going to have the Boltzmann weight of each coloring as an exponent of this variable W. So here we're summing over all of our X colorings. So at the end, we're going to get a polynomial in the variable W with the powers indicating the Boltzmann weight of the coloring. So before we take a look at an example where we compute this enhancement to the Psyquandle counting invariant, we should note that if we have X being a Psyquandle and we have our Boltzmann weight for X, so these are the pair of functions phi and psi, then the polynomial that we've just defined is in fact an invariant of singular knots and links. And this is by construction. In a similar fashion, if we have that X is P1 adequate, and we have that the Boltzmann weights are P1 adequate, then the polynomial we get is in fact an invariant of pseudo knots and pseudolinks. And again, this is by construction. So let's go ahead and take a look at an example. So a fairly simple example where we compute the enhanced invariant, and we see that we actually get additional information that's not presented in just the cardinality of the set of X colorings of a knot by a Psyquandle. So in the following example, we're going to be picking the following Psyquandle structure on Z5. So Z5 is going to be our set, and the operations that we're going to be defining are the following. So here we're picking an Alexander Psyquandle, so we have nice expressions for our operations. We're also going to have some Boltzmann weights on this Psyquandle, and we're defining phi and psi to be maps from X cross X to Z4, and they're defined by phi of xy is equal to 0 for all x and y in our Psyquandle, and psi of xy is equal to 2 for all x and y in our Psyquandle. So in this example, we're using fairly simple Boltzmann weights for our Psyquandle x, and so it should be fairly straightforward to check that phi and psi satisfy the axioms for a Boltzmann weight. So I'll leave it as an exercise. So first, we're going to consider the following singular link diagram. So this is representing a singular link, and of course, this is oriented. So here we have two singular crossings, and the first thing we're going to do is we're going to fix the ordering on the semi-arcs. So we're going to label them x1, x2, x3, and x4. Once we have the semi-arcs labeled, we're going to follow the coloring rules that we set up for Psyquandles. Once we use our coloring rules, we get the following system of coloring equations. So now, since we're using an Alexander Psyquandle, we have nice expressions for both the under dot operation and the over dot operation. So we go ahead and we use our expressions. So here is our system of coloring equations. So now it's a matter of solving for x1, x2, x3, and x4. The number of solutions to the system are going to correspond to the number of x colorings. So when we do that, we can identify each x coloring in the following way. So it's going to be a 4 tuple where each x1, x2, x3, x4 gets mapped to specific elements in our target Psyquandle. So here we list out the colorings of our singular link, and we have 5 of them. So the next thing we want to do is we want to compute the Boltzmann weight contribution of each one of these X colorings. So the way we do this is we assign our weights at the singular crossings, and we're using the weight contribution rule that we set up for the Boltzmann weights. So here we have 2 singular crossings, so we're using psi in each one, and it's going to be psi of x4, x1, and psi of x3, x2. So recall that psi is equal to 2 for all x and y in our Psyquandle. So here we get that the Boltzmann weight of each coloring is the same. So each one is 4, and this is done mod 4. So what we have is the following contribution to our polynomial. So we're going to have w to the power 4, which is just going to equal 1. And so we get just 1 as a contribution from each one of these x colorings. And so when we sum all of the weights of our colorings, we get the following. So we have that the polynomial enhanced invariant here is 5. So this actually agrees with the counting invariant. So here we get the counting invariant. So what we're going to do next is we're going to consider another singular link, and we're going to compute the X colorings of this new singular link with the same Alexander Psyquandle that we were just using. Once we have the X colorings, we're going to compute their Boltzmann weights, and we're going to keep track of them as powers of this variable w, and we're just going to add all of them up to get our polynomial invariant for this new singular link. And in this case, we're going to see that the Psyquandle counting invariant is exactly the same for both of these singular links. But when we consider the enhanced polynomial invariant, the polynomial invariant does detect a difference in these 2 singular links. So let's go ahead and get started with the second singular link. So now let's consider this singular link diagram. So this is similar to our first singular link, but here we have one singular crossing and a classical crossing. We still have an orientation on this, and so the first thing we want to do is we want to fix an ordering on these semi-arcs. So let's label them x1, x2, x3, x4. Once we have the semi-arcs labeled, we can use our coloring rules that we set up for Psyquandles to get the following system of coloring equations. Again, since we're using an Alexander Psyquandle, we have nice descriptions of our operations. So we have a nice description of the under dot operation, over operation, and the over triangle and under triangle operations. So if we use our expressions, we get the following system of coloring equations. So again, in order to find our X colorings, all we have to do is solve for x1, x2, x3, x4. And again, we can represent this as a 4 tuple. So each coloring, so each map is going to be mapping x1, x2, x3, x4 to specific elements in our target Psyquandle. So we're going to represent these colorings in the following way, so as a 4 tuple. So once we have our X colorings, we do the same process as before. When we look at the singular link diagram that we're using here, we have a singular crossing and we have a classical crossing. So remember, at a classical crossing, you assign the phi function, and in our case, phi is equal to 0. So there's no contribution coming from the classical crossing. At the singular crossing, we have psi, and that's a constant 2 function. And so this means that for each X coloring, the Boltzmann weight is 2. And so we collect this information as the exponent of our variable w. And then to construct the polynomial invariant, we just sum over all of these colorings. And so we get the following enhanced polynomial invariant, and we're going to get 5w to the second power. And so we see here that in this, we have the counting invariant, which is 5, but this is detecting that this singular link is different from the first singular link. So we have the same counting invariant for both of them, but when we look at the enhanced polynomial invariant, we detect a difference in these two singular links.